Hello everyone, so we're going to continue to discuss graph theory, and the idea today is to dive deeper into these three concepts that I introduced in the previous lecture about cycles and then also briefly degree. And now we're actually going to start proving a few graph theoretic results rather than just defining things. So let's get started, and we're going to get started with degrees. Also, I'm going to label these results, and I'm going to have a website, and the link's going to be in the description. And the website's going to have all the results that we proved and the lecture that we proved them in. And the idea is if down the line I say, hey, this follows through result or by result 10, you can then go on the website and actually see what result 10 was and also which lecture it was proven in, just in case you need a quick refresher. So we did define what degree means before. It's a concept related to nodes. So let's just quickly give you a refresher. So the degree of node V, let's say this is V, W, ZX. The degree of node V is the number of edges incident to that node, which in this case is 3. For W, it's 2. For X is 2, and for Z, it's 1. So it's just the number of edges that the node is involved in. Perfect. And the first result that we're going to prove is actually called the handshaking lemma. And the handshaking lemma says for a graph G, the total degree. So if you add up the degrees, let's look at my example again. If you add up the degrees of all the nodes, so in this case, it's 3 plus 2 plus 2 plus 1, which is going to give us 8. Right? If we add up all the degrees of all the nodes, it is actually 2 times the number of edges. And if you see, we have 4 edges, which also gives you 8. Okay, so that's the result we're trying to prove right here. And this is actually a pretty simple argument. I'm pretty sure a lot of you were just able to figure it out by now, but the idea is any edge E adds 1 to both, adds 1 to the degree of both its endpoints. So if you pick up an edge E, right, it has an endpoint A and an endpoint B. It adds 1 to the degree of A and also 1 to the degree of B, right? So counting the total degree is just counting each edge twice. And there we go. That's the first result. So let's just quickly go over it again. Any edge adds 1 to the degree of both its endpoints, right? So if the edge was AB, it added 1 to the degree of A and then 1 to the degree of B, right? So let's say this was AB. This edge added 1 to this degree and 1 to this degree, right? And so if you're counting the total degree of the entire graph, you're basically just adding this edge twice because you can add it once you add degree A, and then the second time when you add degree B. And this gives us the handshaking lemma. That is that the total degree of a graph is just twice the number of edges, since each edge adds 1 to both its endpoints degrees. So in total, each edge adds 2. Perfect. It was a very simple result, right? And hopefully you were able to follow through. I just wanted to start off with this result as it is the simplest result I know on a graph. So yeah, it's just always good to start with this. But let's move on now to paths and cycles. And we're going to actually prove a result that I mentioned in the previous lecture, which is this result saying if every vertex has degree greater than or equal to 2, then the graph has a cycle, or at least a cycle, right? You could have multiple cycles, but it has at least one cycle. And before we go there, I just want to give you a few other definitions that I might end up using. So what I'm going to do with this proof is actually, I'm going to give you the standard proof, which I think it was actually one of the first proofs I saw in graph theory, and I found it extremely elegant and smart. But the issue with that proof is that a lot of people, when they first see the proof, say, hey, I could not have come up with something like this. And so that demotivates them, right? Because this is decently clever once you see how we're going to prove it. And so what we're going to do is we're going to actually prove it twice. I'm going to give you the standard proof, the super simple proof that's elegant, and then we're actually going to use first principles to prove this exact result again. And what I just want to do is encourage you and show you that even if you can't come up with that elegant proof quickly, you can start reasoning. And once you start reasoning, you will find something that is very close to that elegant proof. Well, the underlying idea is very close. And then you can look at that proof and see, okay, what did I use? And then refine it to maybe end up at that elegant proof. And we're going to see how that works in a second. But for my second proof, I might end up using a few words, and I don't want to confuse you. So what I'm going to do is I'm going to define a few extra things, and we're going to start off with a subgraph. So given a graph G, a subgraph is another graph where the vertices and the edges are just subsets of the original graph. There is one extra thing that I'm not actually mentioning here, is that any edge you choose, let's say that edge is A, B, then A and B both need to belong to this V prime that you had here, right? And so you choose a subset of the vertices and then a subset of the edges where both endpoints actually belong to V prime. Otherwise, it doesn't work. So if I had this graph, 1, 2, 3, 4, a subgraph could be you could choose, let's say, these two nodes or these three nodes, but then you can't choose the edge 1, 2 because 2 doesn't belong to this graph. So you have to choose edges from nodes that actually belong to your subgraph. And I'm missing that here, but just so I just wanted to mention that. So that's what a subgraph is. And then a spanning subgraph is the exact same thing, but the vertex set is actually V. So you take all the vertices and then you just take a subset of the edges. Okay, where I did mention this before, but I now want to formally define it. A graph is connected if for any two vertices, there is a walk between them. So if I have a connected graph, you could randomly pick any two vertices, right? Let's say 1 and 3, and there is actually a 1, 2, 3 walk in the graph. In this case, it would be let's something like 1, 4, 1, 4, 2, 3, right? Up and then down there, and that gives you a walk from 1 to 3. So that is what it means to be connected. I tried to give some intuition about connectivity in my previous lecture. It's just that it's from any node you can get to any other node. So yeah, but now we're going to finally define it. A graph is connected if for any x and y, any two nodes x and y, there is a walk between them. And then the idea of connectivity gives us the idea of a component. And a component is a maximally connected subgraph. And a lot of times people confuse maximally and maximum. So what maximally means that there is no larger subset that contains this set. So if you have, let's say this is the graph. Let's use a different color. This is component 1 and this is component 2. This is a maximally connected subgraph of this graph. In this graph is connected since every node in this subgraph has a walk between them. And same for this subgraph, but there is no walk from a node of this subgraph to a node of this subgraph. When I define so many terms together, it can get confusing. So it's always good to just, you know, get away from your computer for a second. Just think about everything that we just defined. These terms are not super complicated, but you do want to give your brain some time to think about them. Okay, I'm not going to end up I don't think I'm going to end up using any of these in my second proof, but I still wanted to define them in case I do, and it's always just better to know a few extra things. So we have defined components, right? You could have this graph that is not connected as a whole, but you could have these components within it that are connected. And by connectivity, we mean that for any node in that graph, in this subgraph, there is a walk between them. Then we define subgraph, and then within the concept of a subgraph, there is a spanning subgraph where the only difference is that the uh, vertex set is the complete set of the original graph and the edge set is the actual subset. Okay, let's now try to prove this result, and I'm going to give you the standard result, like I said, but then I'm going to actually try to come up with a proof. I don't have a proof written down, but I'm going to try to come up with a separate proof from first principles, and I'm pretty sure I'll end up just using the same idea that I'm going to use and prove the first proof of this lemma. But the idea is, like I said, you don't need to come up with a great proof at the first try. You come up with the proof, make sure it works, and then see, okay, what are the main ideas I used? And then you can use that to engineer maybe a better proof, a cleaner proof at least. Okay, but let's start with this. And the statement is that if the degree of each node in your graph is greater than equal to 2, then the graph has at least one cycle, right? So if this is true for all v, then it has at least one cycle. Could be more than one, but there is at least one cycle somewhere in there. So let's start by saying, we're going to use contradiction for the first proof. So assume, for sake of contradiction, the degree of v is greater than or equal to for all v. Let me change this. Okay. And G has no cycle. Okay. Consider the longest path. And let's call this path B. And we're going to go from V1, V2 to Vk. So we're now looking at the longest path in G. And I also want to note that G is V comma E, right? So we're looking at the longest path, and you can start imagining what this path looks like. So we have V1, V2. Note each node is distinct. There's no repetition since it's a path. And we go to Vk. Okay. We know that V1 has a neighbor. Okay, so I have not formally defined what neighbor means, but a neighbors, two nodes are neighbors if they have an edge between them. So X and Y are neighbors if they have an edge between them. It's equivalent to the concept of adjacency. Two nodes are adjacent if they have an edge between them, and that's exactly what two nodes neighboring each other means. Okay. We know that V1 has a neighbor. Let's call it Vi, not equal to V2. And this follows from the degree of V1 being greater than equal to 2, as V1 is greater than equal to 2. So it has at least one other node that it is a neighbor of, since it can't have two edges to V2, right? It must have this one other neighbor somewhere that it has an edge to. Okay, so here's the question that I want you to now ask yourself. Oh, well, 1 second, I want to make this clear. Vi. Can Vi belong to B? Right? So can Vi be somewhere here, let's say? Well, the issue then is this edge gives us a cycle because we want to Vi through the path and then back to V1 is going to be a cycle. So in our assumption that we have here that there are no cycles, no, right? Because otherwise we get this cycle that I've drawn here. So vi cannot belong to P. But then note vi does not belong to P. Vi P, or let's write down P, v1 to vk, is a longer path than P. And that's a contradiction, right? Because P was the longest path. And we're done. So we started off by assuming, let's quickly go through the proof again. We started off by assuming that the degree of each node is greater than or equal to 2, and that it has no cycles, right? We then considered the longest path, v1 to vk. This is our longest path. We knew from this original assumption that v1 has at least one other neighbor, and we call it vi. And this is distinct from v2. Vi cannot be v2. The question then is, can vi belong to the path? And the answer is no, because if vi belong to the path, we'll have a cycle, right? And we said that there are no cycles. So vi cannot belong to the path. Perfect. But if vi does not belong to the path, then vi and the path is a longer path than P. And we started off by saying that P is the longest path in the graph. And so this gives us the contradiction. This is a very commonly used technique in graph theory, using these extreme scenarios, right? Like the longest path. And what this does is it narrows down the variability, right? And then you try to pigeonhole yourself into this scenario where it is easy to make conclusions like we did here, right? Because we were considering the longest path. We knew that vi existed. We can quickly argue vi cannot belong to P. Okay, if vi doesn't belong to P, then we can add vi to P, and it gives us a longer path. But P was the longest path, and a contradiction. So we narrow ourselves down to this place where we can derive a contradiction. So a lot of times in graph theory, you might consider the shortest path or the longest path, whichever works better. But yeah, okay. I hear a lot of times, how would I have come up with this? Right, this is not the first thing I would have come up with, and that's true, right? It's this is a decently short proof, and it does the job. It's difficult to come up with proofs like this quickly, and so we're actually going to try and prove this from first principles. I have a few ideas, and I'm gonna hope that they work out. Okay, we're gonna start off by doing the same thing. I'm going to assume for sake of contradiction that the degree of phi is greater than or equal to 2, and G has no cycles. Oh, I am bad at spelling cycles. There we go, cycles. Okay. The first thing I want you to agree with is then for xy that belong to V, to the set of vertices, the xy path is unique, right? There can only be one xy path. And here's why this follows. Let's say this is x and this is y. Let's say there is at least one path because we're assuming our graphs are connected unless otherwise stated. So the graph is connected. So there is at least one path. Let's say there is another path, right? Let's say these are our nodes. And let's say that there is another path. If the path is completely distinct, then you get a cycle. But we said there are no cycles, so the path cannot be completely distinct, right? So it must intersect, but it can't be exactly the same path. So let's say it intersects here, then it could intersect 100 times, right? But the thing is, wherever it first intersects, or even after that, you can get other cycles. But at least if you just follow the first intersection, you get a cycle there, right? This is a cycle here with the first intersection. And so if there are more than one XY paths, I will get a cycle. I won't get a cycle including XY unless the paths are completely distinct, right? But even if the paths are not completely distinct, if the paths look something like this and then just follows here, I will still get one cycle. And so that cannot be true since G has no cycles. So every XY path must be completely unique. Okay, if you don't agree with me, sit down, think about it for a few minutes. Believe me, once you start just thinking about it, give it a few minutes, just some time, it'll start making more sense. Okay, so this is the first conclusion. Let's call it one. Every XY path is unique. Okay, here's what I want you to do next. Root G. And if you are from a CS background, you might know what I'm saying here. So what you're going to do is you're going to choose a node R in G, and then you're going to write all the neighbors down of R, and then so on, right? You're going to recursively just do the same. And so you're going to pick one node and then root the graph from that node. And we're going to actually establish a naming convention for all the other nodes other than R. We're going to call them vi root R, root G at R. R is any node. And we're going to come up with vi jk. I is, well, before we do that, there's a few other things I want to do. We're going to label left, well, we want to arrange this rooted structure such that it's from it has the longest paths to the left. So we're rooting R, right? We're creating this tree-like structure if you're from a CS background, and we're doing so such that the longest paths are to the left. So the longer the path, the more to the left they are, and so the longest path is going to be to the left. And you instantly see I am kind of using this idea, even though I'm not going to use exactly the same proof. Okay, longest paths to the left. So we're going longest to shortest, left to right. So longest to shortest, left to right. Right, so the longest path is to the left. Perfect, that's the first thing I want to do. And then the way I'm going to label each node is I'm going to call each node vijk. I is the child of R, the node belongs to. And so the idea is if the node belongs to this branch formed by the child of R, then it's going to have that number, whichever branch this is. We're going to label left to right as well. Label left to right. And then J is going to be the depth in the branch. And then K is going to be left to right labeling. Okay, this might look a little complicated, so let me just explain. So this, for example, is going to be V1 since it's the first child of R. It's depth 1 since it's within its family. It's the first layer. And then it's the first node, so this one's going to be V111. And so this one's going to be V12 since the depth is 2. And then the third one is, okay, in this level here, which node is this? And so this is 1. And so this is V122, V123. And then if you look at this one, it's going to be so this one's V211. This is going to be V221. Then V222, and then so on. I hope this is starting to make more sense. So we have this, we take the graph, we root it, we have the longer paths to the left, and we have established a naming convention for each node, just so it's easy to refer to them. How many more of these sheets do we have? Okay. And so now I can make this work, right? So remember that the longer paths are to the left. Consider, so what I did is I've just given you some structure, right? This is way more structure than we had in this previous proof. And the reason is because I'm trying to prove it more from first principles. I'm giving you a foundation here. And then within this foundation, I'm going to try and prove the result, right? And what we're trying to prove is, just in case you have forgotten, if the degree is greater than or equal to 2, then G has at least one cycle. Okay, so we have rooted the graph. We have the longer paths to the left, and it's ascending or descending from there. So the longest path is to the left, and then we're descending from there. And we have also agreed that every xy path is unique. Okay, now I want you to consider the leftmost node. Consider the leftmost node, and let's label it. It's going to belong to branch 1, so it's going to be V1, let's say J bar, K bar, right? So this is the leftmost node. So let's see if it looks like, if this goes on to look like this, then it is right here. It's the leftmost node, right? And I also want to note this G is finite. So G is actually finite, right? It can't go on forever. So we're considering the leftmost node, and we have given it a name. It's V1 J bar K bar. Okay. For any node, with J greater than or equal to J bar, the unique for any node, let's give it a name. Well, that's fine. For any node with J less than or equal to J bar, any node anywhere in that entire graph, the unique path from V1 J K must use its direct parent. Okay. So what am I saying here? For any other node, right, in this graph, note that the J index of that node must be less than or equal to J bar, since J bar is Vi J bar K bar is the leftmost node, and so it's the longest node. So any other node might be at the same depth or a depth less than it. Okay, so for any such node, the path from our node must use its direct parent, right? And like we said, there is a unique path. All other nodes are either above it or to the right of it. So it must go up, or well, there is at least one path by going up and then do that node by traversing through this structure. And since there is only one path in this graph, as we have argued here, that is the only path. And now you can see where I'm going to go with this. 1 second. But then the degree of contradiction. And there we go. So the issue is, this is the leftmost node. This is the last node. The graph is finite. There is nothing below it, but everything above it and to the right of it, there is a path through its parent, right? If there's a node above this node, this is our node V1 J bar K bar. Any node above it and to the left of it, there is a path to any of those nodes, this node, this node, this node, any node through its parent, but the paths are unique, like we argued here. But then how is it getting its second degree? Because it can't have any edges to these other nodes because there is only a unique path, and that's through its parents. Okay, then the degree of this node is 1. And that contradicts that the degree is greater than or equal to 2. And we have a contradiction. This proof is lengthier. Well, like I said, just give it some time sit down, think about it, work through it, the idea does work and it gives you a contradiction and gives you the same proof. This proof, the original proof, is way simpler, but if you start looking at this proof, you can arrive to another proof that might look something more elegant and similar to this simpler proof that I've given you. So yeah, we have now started proving a few basic results. We proved this lemma, and then we proved the handshaking lemma. The next part of this lecture is just going to be more proofs. We're going to go through some more results in or involving paths and cycles. And then after that, we're going to move on to connectivity as a topic.